Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, can that robot work safely in industry? And how does that thing work? Hello everyone, welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is about manufacturing robots and how businesses and university researchers can work together to bring new robotics and AI innovations into industry. Before we get started, I'd like to remind you to subscribe to Robot Talk through your favourite podcast provider to make sure you're the first to hear the latest episodes. Another way to find out about new episodes is the email newsletter, which you can sign up to by going to robottalk.org. So, with all that said, let's get on with this week's interview. I recently had a really interesting chat with Gianmarco Pisanelli from the Advanced Manufacturing Research Centre about how to promote the safe and intuitive use of robots in manufacturing. This week, I'm talking to Gianmarco Pisanelli, a tech fellow in robotics research at the University of Sheffield Advanced Manufacturing Research Centre, whose work focuses on collaborative workspaces, multi-robot systems, and robotic simulations for industrial robots. Hi Gianmarco, great to have you on the podcast.
Hi Claire, thank you for having me.
So you work at the Advanced Manufacturing Research Centre in Sheffield, as I said. So for listeners who aren't familiar, could you explain a bit about what the centre is all about?
Sure, yeah. So the AMRC was born over 20 years ago, I think in 2001.
Okay.
And it was born as a collaboration between Professor Keith Ridgway of the University of Sheffield and a businessman called Adrian Allen. Together we were working on a project with Boeing, and they realized that there wasn't really a direct bridge between university and academia research and industry. So their idea was to sort of create this bridge and to connect the lower TRL research that sort of happens in university and give it sort of a sprint towards higher TRL for industry, exactly. And that's how the AMRC was born, sort of following the Fraunhofer model that existed in Germany that didn't really exist in the UK.
Okay.
We focus mostly on research that goes from TRL 4 and up to sort of 6. There have been some examples where we've worked on TRL 7. But usually 6 is where we stop, and then we hand the projects to integrators or to other industries.
Okay, so TRL is technology readiness level. Can you kind of explain for the listeners what those different numbers are?
Yes, yeah, of course, yeah. So the TRL is a scale that, as you said, is the technology readiness level, and it goes from 1 to 9. And where 1 is just an idea, it's a concept.
Okay.
And it can, usually start at university. It could be like a PhD thesis, or even before then, just a broad idea that someone's got. And then TRL 9 is something where you've got final mass production and the commercialization product. So you've got something that you can sell and you can buy off Amazon or whatever retailers. So we work with something that's sort of 4, which is just outside the lab. So you're trying to, it's not as controlled environment as a lab. You're just trying to have facilities that's more representative of something that's a bit more abstract. There's not as a controlled environment as a university lab. And then up to 6, when you can do sort of a prototype or something that sort of is a proof of concept for industry.
Okay, that sounds like a really exciting point in the process to be kind of to be working at.
Yeah, absolutely. And to give you an example of the sort of projects that we work on, so we started as just with Boeing. They were sort of part of the founder of the AMRC. But now we've expanded. We're part of the High Value Manufacturing Catapult, which is sort of a network of research centers that focus on high value manufacturing around the UK, and there is government funding, so we get 1/3 of our funding from the government.
Okay.
And as part of that, we can sort of direct our own research in what we like to do within limits, because obviously it has to be manufacturing, has to be applicable for research in manufacturing. But then that's just 1/3 of the funding. Another third comes from direct sort of engagement with companies. So we work with loads of SMEs, very small companies that can have sometimes even up to 1 or 10 people in the company. But we also work with very big conglomerate, big companies like Boeing, Airbus, Rolls-Royce, JLR, and many more. And we also got lots of our partnership or our member schemes where we've got lots of companies sort of pay a fee every year with different rankings. And according to how much they pay, we've got 3 tiers. And according to how much they pay, they sort of get a number of votes every year for projects that we pitch. So we pitch projects to them, and then they decide what sort of all that money is put together in a pot. And then at the end of the year, all the members can vote on what projects we sort of work on.
Cool.
And then finally, the third sort of way we get funded is through bids and grants, very similar to what universities do. And we collaborate with many universities, both in the UK and around Europe and around the world. And we apply for funds like Horizon or EPSRC and all the many more that are around there.
Okay. So where does the initial seed of an idea for a pitch come from? Is that very much directed by the research that's going on in universities?
So it's a mixture. We've got different themes and we've got different groups. Because actually, I didn't mention this. So we've got, because we've grown quite a lot, and now we've got between 500 and 1,000 engineers and support staff. And we scattered all around Sheffield initially. We've got different centres in Sheffield, in the manufacturing park between Sheffield and Rotherham. And then in the past couple of years or more, we've opened a site in Wales and another one in the northwest, very close to Preston. But we specialise in different things. So where I'm based is Factory 2050, and we are the integrated manufacturing group, and we focus mostly on sort of robotics and automation, digital manufacturing, discrete event simulation, and smart factories. But then we also have other centres that focus on casting, composite material, medical, design and prototype, and additive manufacturing, and many more. So we've got within the different centres, we've got experts, like usually we've got tech fellows or tech leads that sort of are expert in the area, and they try to sort of steer the direction of the research that we do. But also we encourage even junior members of staff to sort of come up with ideas, because sometimes if we have someone that's just joined from university that's so energetic and they're so full of ideas fresh from university, and they're sort of the best people to sort of pitch for ideas. But other times the idea comes really from a project that we've done with a customer, with an SME, and we've realized that actually the project is done and dusted, but there's more we can do. We can sort of bridge the gap even more on that. And finally, yes, there's also direct research that we do with that comes from university. So I'm also the theme lead for manufacturing at Sheffield Robotics, which is a network of students, researchers and lecturers at the University of Sheffield and University of Hallam. And I sit on the exec board, and what we try and do is we try and stir the research around robotics between both universities. And it's sort of a great asset for both ways. So for us at the AMRC, we can see what sort of research is happening at university, and we can try to sort of push that research towards industry and make sure that it's industry ready. And equally, we can help university understand what sort of research is required by industry, because sometimes there is that detach between the two, and sometimes research is done just for the sake of research, because it's an industry challenge, but there are not many applications in the real world. So by doing this sort of interaction between the two and being this sort of bridge between the university and industry, basically we get benefit in both sides.
Yeah, it sounds really interesting place to work. So if I think back, some of the first robots I ever heard about, when I was a child, were those big industrial robots on car manufacturing assembly lines. So how far has the field of manufacturing robots come since then?
Yeah, so surprisingly, actually, it hasn't changed much.
Okay.
So if you think about it, all those big robots, industrial robots, that sort of what started the Industrial Revolution. I guess the third Industrial Revolution. Some may say it's the internet, but also like robotics is sort of what the all sort of automation is up there as well. So they haven't changed much in terms of what they look like. So I think the official first robot is recognized as the first official industrial robot is the Unimate robot.
Okay.
And if you look at it, it's still a combination of rotational joint and some linear joints it still had. But pretty much is a very similar sort of mechanical structure that hasn't changed much. Obviously, in the past couple of years, a bit of perception has been integrated, so robots are being more capable. So there's a vision that it's used quite widespreadly in the assembly line. But that's pretty much it. When it comes to industry, and especially in the assembly line, the production line, most robots are still pre-programmed. They're still taught by point-to-point sort of motions. Sort of they move to a point, that point is taught, and the process is sort of specialized and it's is a very constructed environment, it's very stable environment and highly constructed where everything is always the same. So as soon as there's a bit of uncertainty or a bit of a change in the process, the robot will fail.
Yeah.
We've noticed in the past few years there's been a massive jump with AI and a massive improvement with what AI is capable of doing. And if you look at university labs, there's a lot of applications of that. Lots of robots are quite smart. They use AI, large language models, or very clever image recognition software. But that's not really implemented in the industry. So there's a big mismatch between what happens at the moment in the university and what industry use. And that's what we're trying to push as well at the AMRC. We're trying to make sure that this sort of, for example, AI is implemented in industry as well. But there are quite a lot of obstacles that we have to come through. The main one is standards, because when it comes to industry, you have some standards and some regulations you have to follow.
Sure.
And obviously, they're not up to date and they don't envision the use of AI. Sometimes it's also the latency, because when it comes to sort of these processes, they're very power intensive. When it comes to computational intensity, they use lots of power, computational power. And it's amazing I can do all that in like a fraction of a second, but sometimes that's not fast enough for industry. You might need something that is still a bit faster than that. So yeah, there's quite a lot of hurdles to get around, but hopefully we'll get there soon.
Yeah, definitely. I mean, one of the things that I hear a lot talking to researchers working in universities is kind of the push for more collaborative robots that, really work with people rather than behind a cage or whatever. And this links into an audience question that we had from Jake on Twitter, who says, what's the most significant barrier to widespread adoption of collaborative robots in manufacturing, and how can we overcome it?
Yeah, so there's been I think the past maybe 10 years ago, a bit less, cobots was what everything was talking about. It was a big sort of push for cobots and everyone wanted a cobot. And if you look around, actually, even us at the MSc, we've purchased quite a few cobots and many industries have started using them. They bring quite a lot of benefits. Firstly, in cost. They're much cheaper compared to conventional industrial robots. And in fact, it's sort of a good entry-level sort of robot for SMEs, for smaller companies. And one thing, I think one of the biggest issues that cobots have managed to solve is not so much around the safety, but is on the sort of ease of use of robots.
Okay.
They're extremely intuitive to use. And compared to industrial robots, when you need intensive training and you need to be trained with every single robot from a specific sort of language, to every proprietary language every robot's got. Cobots seem to be quite simple. Usually you've got a tablet, they can just sort of click a few buttons and that. You can just control the robot. But then, when it comes to safety, I'm not quite sure they've solved all the issues that they promised to solve.
Yeah.
The main example, and you probably heard of this quite a lot, is, the robot's safe because it's got force sensors at each joint. So if there's a collision, the robot will just immediately detect the collision and will just stop, and it won't hurt anyone. But then it all depends on the end effector as well. So if you give a robot a sharp object, that robot stops being safe, because something that's very sharp and pointy, it can just, even if it gently touches someone's eye at very low forces, it's still doing a lot of damage. So there's a lot of in uncertainty around the safety. And also, I think safety systems are still a bit limited. I don't think we've got safety systems that are capable of understanding. So at the moment, what we've got is light gates, where the robot will stop if detect a person that's sort of broken the light curtain that's projected by the gate. Or sometimes you can have safety scanners, where they're usually like sort of 2D scanners, where someone enters that zone first, it becomes lower. And then if you get much closer to it, it will just stop. And then sometimes you can also have mats that are sort of set on the floor, and then if they can detect human presence by weight.
Okay.
And so if you go into certain areas, the robot will stop. But then that sort of is quite limiting. You can't do much. So first of all, there's a whole area that you're sort of forcing the person to not be around. For example, what we would need ideally is something that can use, for example, cameras or other trackers to understand human intention. If the person can be detected and the action can be predicted before, so the robot can understand if someone, maybe it's coming into my area, but I can see that the person is not going to approach me, is actually just walking past. Or sometimes there's research that's looking at understanding humans' emotion. Because if you look at someone's face, you can recognize that person is scared. You're scared that something is about to happen, and that's your facial expression is a much quicker representation of what you're thinking before you can even express it. So ideally, if you can use this integrated system into a safety system, you don't even need to tell the robot to stop. You don't even need to press the e-stop button, because the robot will immediately know, that person is scared, something's gone wrong, I'll just stop. Equally, the other side is something that is not really talked about. So there's a lot of focus on trying to understand the humans' actions and interaction with the robot. But then there's not quite a lot of information or sort of studies on how to communicate what the robot intention is. Because a robot programmer obviously knows exactly, and he spends probably hours and weeks and days and months programming the robot. So he knows exactly what the robot is about to do. But sometimes the operators or a technician is not so much aware of what the robot is doing, or even just a person that's walking past. So there should be more research on trying to communicate what the robot action is. So we started doing some research where we just like using lights or projections, we can just communicate the intention of the robot, so the robot can tell, I'm about to perform this action rather than this one. And that also helps that sort of human-robot interaction when the person is a bit more aware of what the robot is about to do, and that sort of enhances the trust that the person has on the robot system. And that trust, we found, is quite a key factor on sort of safety, because if you trust the robot, you can feel more safe around it, and you can also do more activities around it. And then also you have, again, it's quite obvious, but more trust on the capability of the robot. So it becomes inherently more safe.
Yeah, that makes sense. Yeah, I guess naively, when you say like collaborative robot in manufacturing, I kind of think of like a robot that is like a coworker who you work side by side with, and like it doesn't have to be it doesn't have to turn itself off when you walk near it, right? Like your coworkers don't just stop working when you come over to say hello. I guess some of those things you're talking about, and maybe integrating a bit more intelligence into the system would be cool. But I appreciate that's pretty challenging, especially when humans are complicated, unpredictable beings.
Yeah, absolutely. And that goes back to the previous point that I mentioned, that safety is a highly regulated field, and regulatory bodies, unfortunately, are quite underfunded. So we've worked a lot with them, and they've got very limited staff. They don't have enough money to work. So what happens is sometimes they're years and years, sometimes decades behind. So even if there's a new technology that is invented and it uses AI, it can predict what a human is doing, and it's very safe. and it's been tested in a lab and is confirmed it's safe. Well, there's no regulation that will allow anyone in the industry to actually use it because, it's not implemented and the regulatory body is not aware of this. So what happens is, because there's no regulation that sort of it can be certified against, no one in the industry will use it because they won't be protected if anything goes wrong. So I think that's one of the biggest challenges. And what we try and do at the AMRC now, we try and engage with the regulatory bodies a bit more. So, for example, the HSC, we've got good contacts with them, and we try to, from the beginning, when we've got a new idea, we try to sort of contact them. I even pitch the idea to them, because sometimes we've got a better idea of what the health and safety sort of regulations are. But also, equally, they're aware of what we're doing, and they can sort of make sure that the next regulations are in place to cover that aspect.
Yeah. I guess it's really difficult as well to like demonstrate the absolute safety of a system that's using AI, because it's not going to respond in exactly the same way every time, right? That's what's nice about a machine, is you can say, well, I know it's safe because if this happens, it will do this. But with an artificially intelligent robot, it's like, well, it will use its judgment.
Yeah, exactly. Yeah, that's another big issue. Yeah, you're right. So as you said, conventional machines, they might be quite limited, but they're very deterministic. One input can have the same output every single time. AI is a black box, and it's very hard to tell what it's going to do next. There's some research that we're trying to do on trustworthy AI. So something that we can guarantee that can be sort of safe, or not even safe, just predictable, making sure that, because obviously AI is highly stochastic in nature, and it's pretty hard to predict what it's going to do next. And that doesn't really agree with safety. Obviously, you need to make sure that you need to know exactly what's going to happen. And I think that's another big challenge of implementing AI when it comes to safety. And I'm not sure we're going to solve that anytime soon, to be honest.
It's a big one. So you led the development of an innovative robotic coil manufacturing method for high-end electrical machines. So can you tell me a bit about that project?
Yes. So that's one of the sort of initial projects that work here at the AMRC. That's part of the FEM Hub, which is the Future Electrical Manufacturing Hub. And that's a hub that was founded as part of an EPSSC grant that we won. And it's a collaboration between the University of Sheffield, University of Strathclyde, University of Newcastle, the MRC, and then the AFRC. So quite a big university centres around the UK. The aim of the hub was to sort of enhance the manufacturing of electrical machines, specifically for high value and high-end electrical machines. So something that you would see in Formula E cars or even flight. Now, when it comes to sort of the power density required for flight, specifically for flight, the targets that have been imposed by governments around the world and the EU are quite ambitious, and we're nowhere near there. So what the hub was looking at was how can we make sure that this sort of challenges, these targets are met. And I remember exactly how many £1 million it was, but it was quite a big project. And we're looking at different aspects of the electrical machines. What I was focusing on was sort of the winding, because obviously electric motors conventionally made by two active components. One is the winding, basically the copper that is wound around the stator, and the other part is the actual core, the iron, that has magnetic properties. And the combination between the two is what gives you the rotation and the torque. So conventionally, these windings are generated by sort of CNC machines, and they're very accurate, they're very fast, they're very precise. But the problem is they're very specific and they're very costly. So if you were to change the sort of the shape, the size, or even the type of winding that you want to create, you would have to redesign the whole machine, which is very expensive. Now, when it comes to research, when you're trying to build something that is novel and has never been created before, you have to test, you have to create different prototypes. And conventional machines were not appropriate. So what we did instead, we thought the sort of flexibility, firstly, was introduced in manufacturing thanks to robots. Why can't we try and apply robots to this instead? So we bought two robots, we put them in a cell, And we had sort of one holding the stator and the other one doing the sort of winding motion.
Okay.
We created an end effector that could just feed the wire onto the part. And then we had an all clever system on top of the robot that can do sort of tension management.
Okay.
Because the tension that is applied during winding is quite crucial. Because if you apply too much tension, it could damage the wire, it could elongate the wire, causing more losses in the electrical machine. While if you don't put enough tension, the wire that is deposited onto the stator just becomes wild and it doesn't stay put where it's supposed to. And that's pretty much the sort of method that we developed. And we've published a paper and we demonstrated that basically it's possible to use robots to do winding of electric motors, albeit mostly for prototyping, not so much for mass production, because when you compare the speed of the processes, conventional processes are exponentially faster. But we're not interested in sort of making the process faster. We're just interested in trying different types of winding, and robots were the perfect solution for that.
Yeah, brilliant. It sounds like an interesting kind of problem-solving exercise that must have been quite fun to work on.
Fun is an interesting, but I wouldn't have used that because controlling wire was a real challenge. And because usually when it comes to robotic systems, you first start with simulation, and you want to simulate the system first to see how to behave and how you want to build the cell first, and you basically test all the programming in simulation. Now, when it comes to wires or cables, because virtually they've got infinite amount of joints, you can't really model that because each joint is sort of 1 degree of freedom in a simulation sort of program. And if you start adding infinite amount of joint, the kinematics model of a matrix becomes basically infinite.
The computer just falls apart.
So yeah, it's basically almost impossible to do that problem in simulation. So and then we had to just start experimenting with it and start trying winding, and it was a very challenging problem.
One area you're focused on is developing more intuitive robotic interfaces for manufacturing robots. So tell me about some of the interfaces you're currently working on.
So one of the interfaces that we sort of developed was what we called ROSI2.
Okay.
ROSI stands for ROS in an industrial environment. So
and ROS is the robotic operating system.
Operating system, yes. And the reason why we called the project that was that we realized that ROS is very popular in academia, but it's not really used in industry yet. Okay. So we were trying to sort of push that. And as part of the effort, we also joined the ROS Industrial Consortium in Europe and sort of tried to follow the standards, and we help and give back to the community. So as part of that project, we developed sort of a framework for digital twins. And so we can have a digital twin that for any robot that's ROS compatible could just be automatically implemented into this or uploaded into the digital twin environment. It'd be a collaborative robot, 6 degrees of freedom, 7 degrees of freedom, a mobile robot, an AGV. And it could just be controlled from this Unity environment. So it could just drag the robot in the simulation environment and the real robot would respond. Cool. On top of that, we built a sort of augmented reality framework and a speech interface. And the reason why we went for those two was because we wanted to replicate something that is as close as possible to human-to-human interaction. And human-to-human interaction at the end of the day is a collection of verbal, obviously, communication, but also a combination of gesturing and pointing. And augmented reality was the perfect sort of in between that. So what we can do is you can put some goggles or some augmented reality goggles on, like HoloLenses do, and you would have a virtual projection of the real robot on top of the actual robot. And using your fingers, you can just sort of drag the robot around and execute a motion in front of you with augmented reality with the goggles. And the virtual robot will move. And then if you're happy with it, you can also execute the motion, the robot will actually move. And that gives you sort of an idea if the motion is sort of safe to do, or if the robot is going to be out of bound, and you can visualize in front of you. And then finally, you've got this sort of interface that is a speech interface where you can just speak to the robot and ask for sort of a request, and the robot will give you some verbal feedback, and then will execute the motion.
Cool. I mean, this sounds like every stock photograph of people interacting with robots in industries, you know, the VR headset and the like pinching and moving things around. I'm glad to hear that it's actually happening and it's not just in stock photography.
Yeah, no, it does happen. One thing that we realized though is that I don't think augmented reality is quite there yet.
Okay.
Mostly with the ergonomics of it, because it's fun and game when you use it, but prolonged use causes a bit of headaches and a bit of, some people feel also nausea when they use it for too long. Obviously, I know there's been, I think Meta's releasing a newer augmented reality goggles that are similar to glasses. So we'll see how that goes. But I think what we tend to use now is tablets or phones. We just use the cameras and use the augmented reality through a phone or a tablet, because that doesn't seem to give as many headaches as augmented reality goggles do.
Yeah. Your work sounds really varied and fascinating, and I could talk to you about it all day. Gianmarco, it's been fascinating speaking to you today. I've been chatting to Gianmarco Pisanelli from the University of Sheffield Advanced Manufacturing Research Centre. Thanks, Gianmarco.
Thank you very much, Claire.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And if you've got a question you'd like me to ask one of my future guests, you can contact me on social media at Robot Talk Pod, on Patreon at patreon.com/Claire Asher, or at robottalk.org. I regularly announce upcoming guests on all those platforms, and I'd love to include your questions in my next interview. I thought you might like to hear a sneak peek of this month's bonus episode.
Soft robotics as a class of technologies can both include wearable devices to help assist people with challenges such as mobility, as well as implantable devices. And therefore, I think it's really well placed to help address the huge challenge we have in the UK, as well as other developed countries, of an aging demographic. People are living longer, which means a lot of the healthcare challenges which can be related to aging are becoming more prevalent, which, as I mentioned, things like mobility can be helped with assistive devices outside the body. And for treatments inside the body, soft robotics can have the potential to make treatments which previously would have been very major operations under general anesthetic, and therefore perhaps not suitable for someone in their older years, even into a day operation, because the materials are more soft and flexible. Smaller incisions can be made through the skin. And then once inside the body, so the sorts of surgical tools Hadi was just referring to, if they can be more flexible and cause less damage to the body, then the patient recovery times can be greatly sped up.
If you'd like to hear more from this bonus episode, sign up as a supporter on Patreon by going to patreon.com/Claire Asher, and you'll get access to the full catalogue of bonus content. Next week, I'm talking to Didem Gerda Brø from Uppsala University about the future of intelligent systems. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.